Chapter 2, Digital Imaging Characteristics. Analog images versus digital images. In medical imaging, there are two types of images, analog and digital. Analog refers to a device or system that captures or measures a continuously changing signal. Digital, recorded as multiple numeric values, are divided into an array of small elements that can be processed in many different ways. Analog signal, wave, is recorded or used in its original form. So this is kind of the difference between analog watch, which can represent every possible time of day and uses its hands to continuously move around the face, compared to digital, which only represents a certain number of times. So usually every 1/10 of a second, for example. Characteristics of a digital image. A digital image begins as an analog image. Through computer data processing, the image becomes digitized and is sampled multiple times. The critical characteristics of a digital image are spatial resolution, contrast resolution, noise, dose efficiency of the receptor, and to fully grasp how a digital image is formed, an understanding of its basic components is also necessary. Pixel. A pixel or picture or element is the smallest element in a digital image. And I know that we've discussed pixels before, and when you're looking at the two images to the right, you can see that the first one is more clear, and the second one is if you've ever magnified a digital image to the point that you can see little small squares, then you have actually seen what a pixel looks like. And so if you haven't, you can just look to your right and the image shows you what a pixel is. Spatially, the digital image is separated into pixels with discrete whole numbers only values. The process of associating the pixels with discrete values defines maximum contrast resolution. Pixel size. The size of a pixel is directly related to the spatial resolution of the image. The smaller the pixel, the higher the spatial resolution. Pixel bit depth. Bit depth is the number of bits or pieces of information within each pixel. If a pixel has a bit depth of 8, then the number of gray tones that a pixel can produce is 2 to the power of the bit depth, or 2 to the 8, or 256 shades of gray. Bit depth range for most digital systems is between 10 and 16, or 2 to the 10th, 2 to the 16th, or 2 to the 12th shades of gray. So 10 by 24 to 65,536. Each pixel can have a gray level between 1 and 65,536, which is 2 to the 16th. The gray level is a factor in determining the image contrast resolution. So again, from this information, you're not going to need to know even the range of most digital systems or the pixel gray level. Bits per pixel. So this is just showing you an image that is describing different bits per pixel, so you can kind of see the change of 1, 16, and 256, which obviously is a little bit better of an image than especially the number 1 or first one. You can also use this website listed down below that is a good resource in discussing pixel bit depth. Matrix. A matrix is a square arrangement of numbers in columns and rows. In digital imaging, the numbers correspond to discrete pixel values. Each box within the matrix corresponds to a specific location in the image and a specific area of the patient's tissue. The image is digitized both by position, which is spatial location, and by the intensity, which we consider the gray level. The typical number of pixels in a matrix range from about 512 to 512, 1024 by 1024, and can also be as large as 2500 by 2500. The size of the matrix determines the size of the pixels. For example, if you have a 10 by 12 and a 14 by 17 CR cassette, and both have a 5 by 12 by 5 by 12 matrix, then the 10 by 12 one will have smaller pixels. Matrix size. For a given FOV, the larger matrix size, the greater the number of smaller individual pixels. Increasing the number of smaller pixels will improve the quality of the image. A, matrix size is 64 by 64. In B, to your right, is the matrix size is 215 by 215, C 1024 by 1024, and D 2048 by 2048. So again, this is an example of what a large matrix with a small compared to a small matrix on a large. FOV, or field of view, is synonymous with X-ray field. It is the amount of a body apart or patient included in the image. The larger the FOV, the more area is imaged. Changes in FOV do not affect the size of a matrix. So matrix changes affect pixel size. As matrix increases and the FOV remains the same, the pixel size must decrease to fit into the matrix. Another example of field of view and showing you specifically an area of that large image and changing it to a small image field of view. So pixel size, matrix size, and FOV. The MA relationship may exist between the size of the pixel, the size of the matrix, and the field of view. Matrix size can be changed without affecting the FOV. The FOV can be changed without affecting the matrix size. A change in either the matrix size or the FOV will change the size of the pixels. Exposure indicators. Exposure index refers to the amount of exposure received by the image receptor, not the patient. Knowing how exposure factors impact the exposure index is key to learning to provide enough exposure to the image receptor while limiting exposure to the patient. Manufacturers differ in the way exposure is numerically represented, so it can be difficult to calculate exposure amounts. The clinical world has been calling for exposure indicator standardization for several years now. In 2008, International Electrotechnical Commission published a report titled Medical Electrical Equipment Exposure Index of Digital X-ray Imaging Systems, Part 1, Definitions and Requirements in General Radiography. In 2009, AAPM, or American Association of Physicists in Medicine, released a report titled An Exposure Indicator for Digital Radiography. The AAPM report expressed the need clinically to have the standardization, saying that it will give technologists more confidence in adjusting technical factors while following the ALERA principle. So number 16 of AAPM, an exposure indicator for digital radiography. So its recommendations were to establish an indicator of X-ray beam incident on the digital detector, measure an error curve, indicated equivalent error curve. So display the difference between kind and establish target value of the body part, target equivalent error curve, and deviation index. Display a graphic overlay of the image to show which pixels were used to determine the kind. And again, kind, remember, is equivalent error chroma. Provide appropriate analytical tools and allow for processing image data, Q values, or exposure values normalized to standard beam conditions to be displayed and analyzed on the system console, and provide the ability to assess for processing pixel values. Other recommendations is the relationship between QK values and the standardized radiation exposure incident to the DR detectors required for test of a system performance. It is recommended that this relationship be provided by the system manufacturer over the full range of radiation exposures that the system is capable of recording. For test of system performance, it is useful to view and analyze this for processing image values of acquired test radiographs. It is recommended that systems provide functions to display images without image processing, or what we say as Q values, and then to report the mean, median, mode, standardized deviation, and pixel count of values within graphically defined regions. For testing of systems, it is recommended that manufacturers provide methods to remove the anti-scatter grid without otherwise changing the detector's response, or provide grid attenuation factors to be used in calibration. Air karma. Kinetic energy released per unit mass of air is the measurement of radiation energy, or joules, or J. which is absorbed in a unit of air, so kg. Therefore, the quality kerma is expressed as J over kg, or gray. The gray is used most often in equipment to express this measurement. Hint, hint, the gray is used most often in equipment to express this measurement. When an exposure is made of an IR, the air kerma can be easily read during the processing of the exposure. The standardized radiation exposure, KSTD, is a standard exposure typical of that of an imaging receptor system. The exposure is made with additional filtration that hardens the beam to stimulate patient tissue. These standard conditions for the exposure are used to ensure that the equipment is functioning properly. Indicated equivalent air kerma, so kind. This is the measurement of the radiation that has an incident of the image receptor for that particular exposure. This measurement is derived from reading the pixel values produced by the exposure on the IR. Values are known as for processing pixel values, or Q. This is the median found after certain data correction has taken place, and the median value is then compared to the case STD, exposure to deprive the KIND. This may seem a bit complicated, but the kind can be simply stated as the amount of exposure on the IR. So what is kind? The amount of exposure on the IR. This value will help you determine whether the over or under the IR for that particular body part. Target equivalent air kerma value, or KTGT, is a set of values that have been established by either the system manufacturer or by the system user that represent an optimal exposure for each specific body part and view. For example, there are established perfect exposures for a PA chest, lateral chest, portable chest, pediatric chest, and so on. Each body part and view has its own unique optimal exposure. These exposures are listed in a table by body part and by view. Deviation index is simply the difference between the actual exposure, or kind, and the target exposure, which is KTGT, expressed in a logarithmic fashion. This indicator is intended to help technologists determine whether an image has been under or overexposed. Technologists must evaluate images, and if they are unsure of its quality, they should consult with a radiologist. Radiologists have a higher quality display than what is normally used in the technologist workstations. The deviation index can be used to adjust technical factors, and the image must be repeated. A perfect image according to the D1 has a D1 value of 0.0. If the D1 is negative, the image is underexposed. To raise the D1, +1 increases the technique by 20%. If the D1 is positive, the image has been overexposed. To decrease D1, -1 decrease technique by 25%. This +1, -1 changes the kind by +25% or -20%. +1 is approximately 125% of the intended exposure. -1 is 80% of the intended exposure. Several variances could cause the reading of the pixel values, or Q, to be off. A prosthesis within the image, gonadal shielding within the image, failure of the system to recognize the collimated border, or an unexpected body part in the image will cause the D1 to fluctuate, and the technologist should consult with the radiologist regarding the above image variances. Technologists should continue to use image noise as the true determining factor of image acceptance. These standard values should only be used as a guide. Brightness, contrast resolution, spatial resolution are all image quality characteristics. Brightness. I know we've discussed this many times before, but it does refer to the appearance of the image on a display monitor. No technical adjustment during image acquisition will change the brightness of the image. It is strictly a display quality. Contrast resolution refers to the ability of the digital system to display subtle changes in the shades of gray. Contrast resolution in digital imaging is directly related to the bit depth of a pixel in the image. Spatial resolution, the ability of the imaging system to demonstrate small details of an object. Dynamic range of the image does not equate to higher spatial resolution. Smaller pixels equals higher resolution. Image quality characteristics. For example, an AP&E film screen radiograph typically does not show soft tissue structures on the lateral aspects of the distal femur or proximal tibia of fibula. In contrast, an AP&E digital image shows not only the soft tissue, but the edges of the skin that can be seen as well. This is due to the wider dynamic recording range and does not mean there is additional detail. MTF, or Modulation Transfer Function, the ability of a system to record available spatial frequencies, quantifies the contribution of each system component to the overall efficiency of the entire system. It is a ratio of the image to the object so that a perfect system would have an MTF of 1, or 100%. In digital detectors, when an X-ray photon energy excites a phosphor or scintillator layer, the phosphor produces light. Spreading out of the light will always occur. Light spread reduces system efficiency. The more light spread, the lower the MTF. Noise. Anything that interferes with the formation of the image. Radiographic noise occurs during the acquisition of the image. Equipment noise is caused by detector elements or non-uniform detector responses. And then quantum noise. Noise power spectrum, or NPS, describes the spatial frequency content of the noise as well as spatial characteristics. The higher the NPS, the higher the noise for a specific detector. Signal-to-noise ratio, or SNR, how much noise can be tolerated by the radiologist. As SNR increases, noise decreases, but exposure increases to the patient. Again, repeat, as SNR increases, noise decreases, and exposure increases to the patient. This is showing you an example of low noise compared to high noise. Exposure latitude refers to the range of exposure values the image detector is able to produce. Latitude depends on the image detector. The higher the dynamic range of the detector, the more values can be detected. In addition to the range of exposures and the way the detector responds within that range, images must have sufficient contrast resolution for the signal to be detected. DQE, Detective Quantum Efficiency, describes how efficiently a system converts the X-ray input signal into a useful output image. DQE is a measurement of the percentage of X-rays that is absorbed when they hit the detector. Systems with higher quantum efficiency can produce higher quality images at a lower dose. Amorphous selenium, amorphous silicone, TFT, and charge-coupled device, CCD, and complementary metal oxide semiconductor detector technology has increased DQE over PSP. Chapter 3. Digital radiographic image processing and manipulation. In both photostimulable phosphor, or PSF, and flat panel detector systems, FPD, after the X-ray photons have been converted into electrical signals, these signals are available for processing and manipulation. Pre-processing takes place in the computer where the algorithms determine the image histogram. Post-processing, done by the technologist through various user functions. Photostimulable phosphor reader functions. The PSP imaging plate records a wide range of X-ray exposures. In image formation, using values at the extreme high and low ends of the exposure range would result in a low density resolution. To avoid this, exposure data recognition processes only the optimal density exposure range. Data recognition program searches for anatomy recorded on the imaging plate as follows: finding the collimation edges, eliminating scatter outside the collimation. Information within the collimated area is the signal used for image data. This is the source for a vendor-specific exposure data indicator. Failure of the system to find the collimation edges can result in an incorrect data collection. Images may be too bright or too dark. Equally important is centering anatomy to the center of the imaging plate. It ensures that appropriate recorded densities are located. Failure to do so could result in an image that is too bright or too dark. Histogram, a graphical representation of exposure values collected from the imaging plate. The value of each tone is represented on a horizontal axis. The number of pixels in each tone is represented on the vertical axis. Values to the left are darker. As tones vary toward the right, they get brighter. So hint, you need to know which is on the horizontal axis and which is on the vertical axis. Because information within the collimated area is the signal used for image data, the information is also the source for a vendor-specific exposure data indicator. Image sampling. Plate is scanned, image location and orientation are determined, size of the signal is determined, value is placed on each pixel. A histogram is generated from the image data. Histogram is generated that allows systems to find useful signal by locating the minimum S1 and maximum S2 signal within the anatomic regions of interest in the image. Histogram identifies all densities on the imaging plate in the form of a graph. X-axis is related to the amount of exposure. Y-axis is the number of pixels for each exposure. Graphic representation appears as a series of peaks and valleys and has a pattern that varies for each body part. Example of those peaks and valleys is at the very bottom of your screen in the right corner of this image. Image sampling. Lower energy, KVP, gives a wider histogram. Higher energy, or KVP, gives a narrow histogram. Histogram shows the distribution of pixel values for each given exposure. For example, pixels have a value of 1, 2, 3, and 4 for a specific exposure. Histogram shows the frequency of each of these values and the actual number of values. Histogram sets the minimum S1 and maximum S2, and that becomes a useful pixel values. Histogram analysis. The analysis is complex. Shape of the histogram stays fairly constant for each part exposed, or the anatomy specific. For example, shape of a histogram for a chest radiograph on a large adult patient looks different from a knee histogram generated for a pediatric knee exam. It is important to choose the correct anatomic region on the menu before exposing the patient. Raw data used to form the histogram are compared with a normal histogram of the same body part by the computer. Image correction takes place at that time. The Nyquist theorem. In 1928, Harry Nyquist described a way to convert analog signals to digital signals that would be more accurately transmit over telephone lines. The analog signal could be captured, transmitted digitally, and recreated in analog form on the receiver. In 1948, Claude Shannon presented a mathematical proof of the Nyquist theory. Many scientists have added to and revised the theory. It is often referred to simply as the sampling theorem. The theorem states that when sampling a signal, the sampling frequency must be greater than twice the bandwidth of the input signal so that the reconstruction of the original image will be as close to the original signal as possible. At least twice the number of pixels needed to form the image must be sampled. If too few pixels are sampled, the result is a lack of resolution. Oversampling does not result in additional useful image. This is showing you an example of undersampled or elapsing, and then they're corrected sampled. Nyquist theorem continued. The number of conversations in PSP, electron to light, light to digital information, and digital to analog signal results in loss of detail. Some light is lost during the light to digital conversion because of the spreading out of light photons. Because there is a small distance between the phosphor plate surface and the photosensitive diode of the photomultiplier, some light spreads out there as well, resulting in loss of information. The longer the electrons are stored, the more energy they lose. When laser stimulates electrons, some lower energy electrons escape the active layer. If enough energy was lost, some lower energy electrons are not stimulated enough to escape, and image is lost. All manufacturers suggest that imaging plates be read as soon as possible to avoid this loss. Flat panel detector systems and the Nyquist theorem. Both FPD systems lose fewer signals to light spread than conventional radiography. The Nyquist theorem is still applied to ensure that the sufficient signal is sampled. Because sample is pre-processed by the computer immediately, signal loss is minimized but still occurs. Aliasing occurs in digital imaging when spatial frequency is greater than the Nyquist frequency, sampling occurs less than twice per cycle, information will be lost, and fluctuating signal is produced. It's also known as foldover or biasing. A wraparound image is produced, and the image appears as two superimposed images slightly out of alignment. This is an example of aliasing. Aliasing results in a moire effect. The same effect can occur with grid errors. Automatic rescaling. When exposure is greater than or less than what is needed to produce an image. Automatic rescaling occurs in an effort to display the pixels for the area of interest. Images are produced that have uniform brightness and contrast regardless of the amount of exposure. Problems occur with rescaling. Too little exposure results in quantum model. Too much exposure results in a loss of contrast and loss of distant edges because of detector saturation. Rescaling is no substitute for appropriate technical factors. Danger exists of using higher than necessary mass values because doses will creep up over time. LUT, or lookup table, a histogram of the luminescence values derived during image acquisition, used as a cross-reference to transform raw data or information. As mapping function, all pixels are changed to a new gray value. Image will have appropriate appearance in brightness and contrast, and provided for every anatomic part. LUTs can be graphed as follows. Plotting the original values range from 0 to 255 on the horizontal axis, and plotting new values also range from 0 to 255 on the vertical axis. Contrast can be increased or decreased by changing the slope on the graph. Brightness or density can be increased or decreased by moving the line up or down on the y-axis. This is just showing you an example of that LUT. Quality control workstation functions. Image processing parameters, contrast manipulation, spatial frequency resolution, spatial frequency filtering, which is like edge enhancement and smoothing. So to begin with, image processing parameters, digital systems have greater dynamic range than film screen. Initial digital image appears linear when graphed because all shades of gray are visible. Digitization gives the image a wide latitude. If all shades were left in the image, contrast would be too low. To avoid this, digital systems make use of various contrast enhancement parameters. Names differ by vendor. Agfa uses Musica, Fuji uses Gradation, and Carestream, which is also known as Kodak, uses tone scaling. The purpose and effects are basically the same. Contrast manipulation. Contrast enhancement parameters convert the digital input data to an image with appropriate brightness and contrast. Image contrast is controlled by using a parameter that changes the steepness of the exposure gradient. Brightness can be varied at the toe and shoulder of the curve, removing the extremely low and high density values using a different parameter. Parameters should only be used to enhance an image. No amount of adjustment takes the place of proper technical factor selection. Workstation screen showing contrast manipulation choices. This is just showing you again an example of contrast manipulation. Spatial frequency resolution. This refers to detail or sharpness of the image. Digital image processing parameters allow the technologist to choose the structure to be enhanced, control the degree of enhancement for each density to reduce image graininess, and to adjust how much edge enhancement is applied. Image formation is degraded if improper algorithms are applied. Image manipulation before sending to the picture archival and communication systems, or PACS, reduces the amount of manipulation the radiologist can do. After the image is stored in PACS, all post-processing results in a loss of information from the original image. Edge enhancement and smoothing, which is spatial frequency filtering. Edge enhancement. After the signal is obtained, for each pixel, averaging of the signal occurs to shorten processing time and storage. The more pixels involved in the averaging, the smoother the image appears. Signal strength of one pixel is averaged with the strength of adjacent pixels, or neighborhood pixels. Edge enhancement occurs when fewer pixels in the neighborhood are included in the signal average. The smaller the neighborhood, the greater the enhancement. When frequencies of areas of interest are known, they can be amplified, and other frequencies can be suppressed. Amplification is also known as high-pass filtering and results in increase of contrast and edge enhancement. Suppression of frequency, also known as masking, can result in loss of small details. This technique is useful for enhancing large structures, such as organs and soft tissues, but can be noisy. This is showing you an example of an image without enhancement and with enhancement. Smoothing. Smoothing is also known as low-pass filtering. This results from averaging of the frequency of each pixel with surrounding pixel values to remove high-frequency noise. It results in a reduction of noise and contrast. Low-pass filtering is useful for viewing small structures such as fine bone tissue. Basic functions of the processing system. We'll discuss image manipulation, window level and window width, background removal or shutter, image orientation, image stitching, image annotation, and magnification. And then we'll also discuss image management, which is patient demographics input, manual send, or archive query. Image manipulation. So again, window level, window width, background removal or shutter, image orientation, stitching, annotation, and magnification. So begin with window level, window width. Window level, we know, controls how light or dark the image is, where window width controls the ratio of black or white, or contrast. So user is able to manipulate quickly through use of the mouse. Movement of the mouse in one direction, vertical or horizontal, controls brightness, and the other direction controls contrast. Minimal manipulation will be required on an image with appropriate exposure factors. Background removal or shutter. Underexposed borders around the collimation edges allow excess light to be entered the eye. So we've discussed in the past veil glare, and this still occurs in digital systems. It causes oversensation of a chemical within the eye called rhodopsin. This results in temporary white light blindness. Eye recovers quickly enough so that the viewer recognizes only that the light is very bright. Veil glare is a great distraction that interferes with image reception by the eye. Background removal or shutter continued. In digital imaging, automatic shuttering is used to blacken out the white collimation borders. Shuttering is a viewing technique only. Shuttering should never be used to mask poor collimation practices. Removal of the white unexposed borders results in an overall smaller number of pixels. This reduces the amount of information that needs to be stored. Image orientation. The way the anatomy is oriented on the imaging plate, the image reader must be informed of the part location, head versus feet, left versus right. The image is displayed exactly as read unless the reader is informed otherwise. The cassette must be oriented so that the image is processed to display as expected. Vendors mark the cassettes in different ways. Fuji uses a tape type or orientation marker. Kodak, or again what we call Carestream, uses a sticker. With FPD systems, the position of the part should correspond with the marked top and sides of the detector. Stitching. Stitching is used for anatomy or areas of interest too large to fit on one cassette. Multiple images can be stitched together. Sometimes special cassette holders are used and positioned vertically, corresponding to foot or hip or entire spine studies. Images are processed in computer programs that nearly seamlessly join the anatomy. Computer displays one single image. Process eliminates the need for large like the old 36-inch cassettes previously used in film screen. This is just showing you an example of many different images being taken, and then to the right you see where it would be completely as one image. Again, some more images that were taken separately, and then we see the image stitched where it is completely together. Annotation. You all know annotation. So back when we used film screen radiography, we used to use a marker. So we had grease pencils or permanent Sharpies to be able, and time and date stickers. So this is information other than standard identification must be added to the actual image. So the function allows selection of preset terms or manual text input. Can be useful when such additional information is necessary. Overlay the image as bitmap images. May not transfer to PACS always. So again, that's important information because you're using this a lot as a left or a right, and it may or may not transfer to PACS. Input of annotation for the identification of the patient's left or right side should never be used as a substitute for actual markers. Magnification. Two basic types of magnification techniques are standard with digital systems. One technique functions as a magnifying glass. A box is placed over a small segment of anatomy on the main image. The box shows a magnified version of the underlying anatomy. The size of the magnified area and the amount of magnification can be made larger or smaller. The other type or technique is zoom. Zoom allows magnification of the entire image. Image can be enlarged enough that only parts of it are visible on the screen. Those parts can be seen through mouse navigation. This is just showing you an example of magnification. Image management. Patient demographics input, manual send, and archive query. Patient demographics input. Proper identification of the patient is even more critical with digital imaging. Retrieval can be nearly impossible if an image is not properly and accurately identified. Demographic information about the patient includes name, healthcare facility, patient identification number, date of birth, exam date, and some other pertinent information. Information should be input or linked via barcode label scans before the start of the exam and therefore the processing phase. Functions should be tracked to link the technologist with alterations for accuracy and accountability. The patient's name must be entered, the same for each visit or exam. Problems occur if the name is entered differently. Suppose the patient gives a middle name or initial, and previous exams have only his or her first name. The system will save each version of the name as a different patient. Merging of files can be very difficult, and retrieval of previous files will be difficult as well. The right images must be placed in the correct data files. Manual send. Because the quality control workstation is networked to the PACS, it also has the capability to send images to the local network workstations. The manual send function allows the quality control technologist to select one or more local computers to retrieve or receive images. Archive query. PACS archive can be queried for historical images. Function allows retrieval of images from the PACS system based on the following: date of exam, patient name or number, exam number, pathological condition, or an anatomical area. Example: technologist could query PACS to retrieve all chest radiographs for a particular date or range of dates. Technologist should query retrieval of all of a certain patient's images. Multiple combinations of query fields can generate reports from storage that include many categories of information or a few specific ones.